Hi friends, in our last video we discussed about the orbitals, the shapes of orbitals and the characteristics that define the electronic structure of any atom. Okay, so we discussed that the orbitals are characterized by three quantum numbers. First is principal quantum number, second is azimuthal quantum number, and third is magnetic quantum number. Well, the fourth one is also there, that is spin quantum number. Sometimes we denote it by S or sometimes we denote it by MS. Okay, so we discussed that N denotes or N tells a lot of things about size and most of the things about energy of an electron. L tells us about the shape and also about the angular momentum of an electron. Okay, here ML tells us about the magnetic moment, of an electron, and the orientation of orbital. And finally, MS tells us about spin of an electron. Okay, so we discussed that S orbital has circular shape, P orbital has lobe shape or dumbbell shape, D orbital has double dumbbell shaped, and F orbital has somewhat some complex shape, which something looks like there are two rings over here, or there is one more. Okay, so S orbital has these type of shapes. D orbital, one of the D orbitals has this type of shape. It has one ring over here. This orbital is dz square. Okay, all the D orbitals has this double lobe shape, but one orbital, that is dz square orbital, has a single lobe shape with a ring in between. Okay, and we also discussed that about the nodal planes, about the radial nodes. First of all, we discussed about the radial nodes, and then we discussed that we discussed about the nodal planes, that P orbital has one nodal plane, or the D orbital has two nodal planes, and F orbital has three nodal planes, and one is in this direction. Okay, here. Okay, and also we discussed that the nodal plane is the plane where the probability of finding an electron is 0. So therefore the probability of finding an electron in this plane is 0. Well, to this question or to this statement, one question may pop up in your mind, that if the probability of finding an electron at this nodal plane is 0, then how does an electron jumps from this place to this place? Well, at this point you do not need to think about this. Okay, this is outside of our syllabus, that discussing this topic, so we are not going into that. Fine. So in this video we are going to discuss about energy of an electron and how an electron is filled. Okay, how the electrons are filled in various orbitals, and then we'll discuss some examples about electronic configuration of an atom. Okay. Okay, so while discussing energy, we must keep in mind the factors on which the energy of an electron depends. Okay, so here energy of an electron depends on distance from nucleus, that is n. It also depends on electron repulsion, okay, and also it depends on effective nuclear charge. effective nuclear charge. Okay, so what this effective nuclear charge is, although we have discussed how does the energy of an electron varies with respect to the distance in Bohr's model, and well, these two things are called multi-electronic systems. Okay, so basically these two factors are predominant in multi-electronic systems, that is the systems with more than one electron. Okay, so here, the electron-electron repulsion, as the electrons are filled in the orbital, since we discussed that suppose if this is one orbital, then if first electron is filled in this manner, then the second electron will be filled in this manner, in order to minimize the electron-electron repulsion. Okay, so the spins of both of the electrons are going to be different, but even if the electrons are filled in different orbitals, for example 2p, and only if 3 electrons are there, then they will have the same spin. And because of the distance factor, the repulsion between the electrons will be there. Okay, so therefore there must be some other factor as well besides n on which the energy of an electron depends. So what are those factors? So the second thing is electron-electron repulsion. Okay, and now the effective nuclear charge. As we move away from the nucleus, then in multi-electron system there must be some electrons in front of the one electron in which we are considering. Suppose if this is the nucleus and this is 1s orbital in which 2 electrons are there, okay, and here this is 2s orbital in also 2 electrons are there. Okay, so now these 2 electrons cannot see nucleus directly, although we have just shown the exact location of an electron, but the location is not exact. Okay, so please bear in mind this is not the exact location, this is just for the representation. So because of these 2 electrons, the electrons of 2s orbitals cannot see the nucleus directly, and if they cannot see the nucleus directly, then there is something which is hindering them, and that thing which is hindering it is the electrons of 1s orbital. So although the distance between the nucleus and the 1s orbital electron is very less, they can see directly. So there is nothing which is hindering the force of attraction between this nucleus and the electrons of 1s electron. But in case of the 2s electron, there is some extra electrons in between the 2s electron and the nucleus. Therefore, the force of attraction between the nucleus and the 2s electrons are hindered. Okay, force of attraction is hindered. Okay, so here in this case, the force of attraction, the force that I am talking about is this. Okay, so the force of attraction is hindered because of these 2 electrons. Now, this is what we have spoken about the 2s electrons. But now coming to 2p electrons, suppose this is the 2p electrons. Fine. Suppose this is the 2p electrons. There are going to be in total 6. Okay, so now the force of attraction between nucleus and these 2p electrons are further hindered by 1s electron and the 2s electrons. Now if you see and also this hindrance which 2p electron is facing is amplified due to the extra number of electrons if we compare it with the hindrance that is being faced by 2s electrons. So now furthermore, if you consider the 2d or if you consider the 3s electrons, then it is again facing hindrance here. If we consider this 3s orbital, okay, so it is again facing hindrance because of 10 electrons. So in total, before 3s orbitals, 10 electrons are already there. Okay, so it is also facing hindrance. So therefore, because of this hindrance, the nuclear charge, okay, the charge which this electron is seeing directly is not what it should be. Okay, so here the charge of nucleus is Ze, because Z number of protons are there in the nucleus. Z is the atomic number. Okay, so here 2s electron faces less charge than it should. Okay, now the charge which should be faced is Ze, but it faces some other charge, that is Z-E. So Z- is known as effective nuclear charge. This thing, this particular thing is effective nuclear charge. Okay, so because of all these factors, because of electron-electron repulsion which we have discussed here and the effective nuclear charge which we have discussed here, so the energy does not entirely depend on N. That's why we used a term that energy, it depends majorly on N in case of multi-electronic species. But in case of hydrogen, remember, even if the hydrogen is in excited state, that is in 3s state, then there is no electron inside and hence the energy is not hindered. Therefore, the energy of all the orbitals in case of hydrogen is same. All the orbitals are degenerate in case of hydrogen atom, but in multi-electronic species such as lithium, beryllium, oxygen, the case is not the same. Therefore, the orbitals are not degenerate. Fine. So here, because of effective nuclear charge and electron-electron repulsion, because of these two factors, energy also depends on azimuthal quantum number, that is L. In order to make the things clear, I'll try to explain to you that in case of 2s electron, the hindrance is some. Suppose the hindrance is X. This is the hindrance. Okay, but in case of 2p electrons, there is going to be some extra hindrance, X plus Y, because 2s orbital is already there in front of it. And in case of 2d, and in case of 3s, there is going to be X, Y, Z, and same it goes on. In case of 3p and 3d, the hindrance will keep on increasing because of the extra orbitals that we are considering. Therefore, it also depends on this factor, that is azimuthal quantum number. And because of this reason actually, so we can say that energy in case of multi-electronic species, remember this all discussion is going on in case of multi-electronic species, okay? In case of multi-electronic species, also depends on L. Okay, so remember this particular statement that it also depends on L. Now, although the exact equation for energy and its dependence on principal quantum number and azimuthal quantum number is a bit complex. In fact, it is more complex than we can think. So therefore, we are not going into it, or we are not going to derive the mathematical expression or so. So we must understand here, the only fact that we need to understand is that energy increases with increase in N plus L value. Okay? So here, the energy will increase, and energy increases with increase in N plus L value. So therefore, N plus L in case of 2p or in case of 3p, here, in case of 3p, N plus L is equals 3 plus 1, that is 4. But in case of 3d, N plus L equals 3 plus 2, that is 5. So therefore, this gives us that energy of 3p is lower than energy of 3d. Okay, so this is the first fact that you need to remember. So because this is going to be the major driving force for writing the electronic configuration of any atom. Okay, so this is the major concept which will write or which will decide the electronic configuration of any atom. So now there is one small fact that we need to discuss, is that the energy of same orbitals decreases with increasing atomic number. Okay, so this is the case. So therefore, because of this particular statement, energy of 3s orbital of sodium is greater than energy of 3s orbital of potassium. Okay, so these are the basic concepts which we need to assign the electronic configuration. Now we are going to take one step further in writing the electronic configuration of any atom. We are going to discuss some principles that were used or that were given in order to be followed while writing the electronic configuration or while assigning the electron to any particular orbital. So there are three principles that are followed basically. First is Bow principle. Many people pronounce it as Au-Bow, but that's not Au-Bow. The correct pronunciation is Bow, although the spelling is different. The second principle that we are going to discuss is Hund's rule of maximum multiplicity, and the third is Pauli's exclusion principle. The third, that is Pauli's exclusion principle, is more, means it contributed more to chemistry as compared to Heisenberg's uncertainty principle. It was like a revolution. Okay, so we are going to discuss these three principles currently, just now. Okay, so the first principle that we discuss is Bow principle. Okay, so this Bow principle, its correct pronunciation is Bow. Remember, the correct pronunciation is Bow principle. Okay, so this says that the electrons are filled. This principle says that electrons are filled in orbitals in order of increasing energy. Okay, that is, it says that the orbital having lower energy is filled first. It says that orbital having lower energy is filled first. Okay, so therefore 1s orbital is filled before 2s orbital or 2p orbital. 2s orbital is filled before 2p, or 3s orbital is filled before 3p. Or okay, so but here, since 2p and 3s orbital have got same value of n plus l, but the energy of 2p is lower than that of 3s because the value of n is lower in case of 2p. Okay, so therefore 2p orbital is filled before 3s orbital. And since the names 2s, 2p or 3d, these are just the names of the orbitals in order of energy. Okay, so here this orbital says that, or before rubbing it, this orbital says that, and as an example, 2s orbital is filled before 2p and 3s. Okay, and 3s orbital is filled okay, so 3s orbital is filled after 2p, although according to n plus l rule they should have the same energy, but it is not so, because the value of n which is lower has got the lower energy. Okay, so here, so suppose in case of an atom of sodium which has atomic number as 11, so therefore let's say in case of sodium there is 11, there are 11 electrons. Okay, so there are 11 electrons. So therefore filling is done such that first 1s orbital is filled, then since there is no 1p orbital, so we will move on to 2s. Then 2s orbital is filled, since there is 2p, so therefore after that 2p is filled, and then since there is no 2d, we will move on to 3s, so then 3s is filled. Okay, so the 1s can accommodate 2 electrons, since an s orbital can accommodate 2 electrons, so 2 electron will get filled here, then 2 electron will get filled here, because s orbital can accommodate 2 electrons, p orbital can accommodate 6 electrons, so 6 electrons will get filled here. So the number is already 10. Now we are left with only 1 electron, so the final electron will get filled over here, although it can accommodate 1 more electron. So in case of magnesium, this is 2, there are 2 electrons here. Okay, fine. So in order to remember it, we can make a chart like we can make a chart as 1s, 2s, 3s, 4s, 5s, there are 2p, 3p, 4p, 5p, 3d, 4d, 5d, 4f, 5f. Okay, so the electron is first filled over here, 1s, then it goes to 2s, then 2p, then 3s, then 3p, okay, then 4s. After 3p, 4s is filled, then it goes to 3d, then 4p, okay, then 5s, okay, then 4d, then 5p, and so on. Okay, so the electrons are actually filled in this manner because of the increasing value of n plus l. So this is the Bohr principle that we discussed just now. So another principle is Hund's rule of maximum multiplicity. Okay, so before explaining this, I would like to tell you that what does maximum multiplicity means. Okay, so the multiplicity here is actually the formula 2s plus 1. So just you do not need to know what s is, what capital S is, but in simple terms, capital S is nothing but summation of all ms. Okay, that is the spins. Suppose if an orbital, suppose 3D orbital is there, and these are the 3D orbitals. One electron is filled here, this is filled here, this is filled here. Then then S will be half plus half plus half. That is 3/2. Okay. Now, if one orbital or one of the electrons is filled in this manner, then the spin is opposite. That is, there is one term which has the number as minus half. So therefore, in this case, this will be half plus half plus half minus half. So the value will be 1. The capital S will be 1. Okay. So therefore, we can say that the maximum number of unpaired electrons will give us the maximum multiplicity. Fine. So this is what's said by Hund's rule. Hund's rule of maximum multiplicity. Okay. It says that the electrons are filled in an orbital. Electrons are filled in orbitals, or electrons are filled in an orbital such that it gives maximum multiplicity. Or maximum number of unpaired electrons. Okay, so the electrons are filled in an orbital such that it gives maximum multiplicity or maximum number of unpaired electrons. So we'll see in the same example of sodium how the electrons are filled in 2p orbital. We saw that in sodium, 2p orbital contains 6 electrons. Okay. So how these electrons are filled? The electrons are filled like, suppose if this is 2p orbital, okay, if this is 2p orbital, then first electron goes like this, then second electron will go like this. Pairing will not start unless all the orbitals are filled. Okay, remember that pairing will not start unless all orbitals are filled. Okay. So here the final, that is third electron will go here in this way. Now there are no further orbitals. Okay, there is no we cannot see the fourth orbital over here. So therefore the fourth electron goes over here with the first one and it starts pairing. The fifth electron here in this way, sixth electron here in this way. So if it would have been 5 electrons only, then the electronic configuration would have looked like this in 2p orbital. If it would have been only 4 electrons, then it would have looked like this. It would have been only 3 electrons, it would have looked like this. Then now there is a catch here. Half filled orbitals or the fully filled orbitals give extra stability to the atom. Okay. So for example, in case of chromium we see that the electron jumps from 4s orbital to 3d orbital. That is, all the electrons are unpaired even in 4s orbital. We'll see later while writing the electronic configuration. Okay. So just remember that half filled orbital or the fully filled orbital gives extra stability to the electrons or gives extra stability to the atom. So therefore this is the statement made by Hund's rule of maximum multiplicity, that the pairing will not start unless all orbitals are filled. or the orbitals are filled in such a manner that gives maximum multiplicity. Okay, so this was Hund's rule of maximum multiplicity. Now, in higher level chemistry, Pauli's exclusion principle plays a significant role. It distinguishes between, we say, fermions. That is, electron is a type of fermion. You do not need to understand what fermion is at this level. There is another type of species called as bosons. Okay, for example, hydrogen nucleus. So we do not need to understand what these fermions and bosons are. But Pauli's exclusion principle differentiated these two. Okay, in higher level chemistry, it really is an asset to the chemist. That is Pauli's exclusion principle. So Pauli's exclusion principle says that Pauli's exclusion principle, okay, it says that no two electrons can have same set of quantum numbers. Okay, that is, or in simple terms, it says that no two electrons can have same value of N, L, Ml and Ms. Okay, so no two electrons can have same value of N, L, Ml or Ms. That is, these four quantum numbers cannot be same for more than one electron. Okay, so this is a milestone actually. So for example, in 2p orbital, suppose this is a 2p orbital. This is 2p. Okay, so if an electron is filled like this and if an electron is filled like this, fine. Since L here is 1, therefore Ml is going to be -1, 0, +1. This is Ml. Okay, and S here is half. This means up spin. Ms is half for this spin and -half for downward spin. Okay, so for this electron, N equals 2, L equals 1, Ml equals -1 and Ms equal plus half. Whereas for this electron, N equals to 2, Ml equals 0, L equals 1, Ms equals plus half. Okay, so we can see that these two electrons have same set of 3 quantum numbers, but the 4th quantum number is different. Okay, so suppose if an electron is here with this spin, okay, then this will violate Pauli's exclusion principle, because all 4 electrons will be same in this case, and that is why the 4th electron, when all the 3 electrons are filled here in this case, suppose, then the 4th electron is always filled with opposite spin. Okay, that is why we fill the 4th electron with opposite spin, because otherwise it will violate Pauli's exclusion principle. So for this electron, the value of N is 2, L is 1, Ml is 1, Ml is -1 and Ms is -half. Okay, so this is the Pauli's exclusion principle, that no two electrons can have same value of N, Ml, L and Ms. Okay, so these are the principles that are followed while writing the electronic configuration of any atom. So we are going to write some electronic configuration of an atom. First we are going to write the electronic configuration of boron, which has 5 electrons. Then we are going to write the electronic configuration of aluminium, which has 13 electrons. Okay. Then we are going to write electronic configuration of calcium, which has 20 electrons. Then we are going to write electronic configuration of argon, which has 18 electrons. Then we are going to write electronic configuration of chromium, which has 24 electrons, and then copper, which has 29 electrons. Okay. So here boron, since it has 5 electrons, then the first 2 electrons will get to 1s. Okay. The next 2 electrons will get to 2s. We write it like this. We discussed in our last video. Okay. And the final electron will go to 2p, and that is only 1 electron. There is only 1 electron. In case of aluminium, there are 13 electrons. So first electron goes to 1s. Second also goes to 1s. The next 2 electron goes to 2s. The next 6 electrons goes to 2p. 6. Now there are 10, still 3 left. The next 2 electron goes to 3s, and the final p electron goes to then the final electron goes to 3p. Okay, so this is the electronic configuration for aluminium. For calcium, the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So there are total of 18 electrons so far. Now the 2 electrons are left. Remember, for 3d, n plus l equals 5. And now for 4s, for 3d, n plus l equals 5, and for 4s, n plus l equals 4. Okay, so therefore the next electron will go to 4s, not to 3d. Okay, so the next 2 electrons goes to 4s. Okay, in case of argon, or if it would have been scandium, that is which has 21 electrons, then the next electron would have gone to 3d. So in case of argon, this is first, let's discuss argon. This is 1s2, 2s2, 2p6, 3s2, 3p6. This is the electronic configuration for argon. And since all the orbitals are filled here, remember that all the orbitals are filled. All orbitals are filled. Okay, therefore it is very stable. Okay, and these type of stable elements are known as noble gases because they are relatively very unreactive. Okay, these are the noble gases. Okay, so these type of elements are called noble gases whose all the orbitals are filled because all the electrons are in a relatively very stable state. Fine. So now let's discuss the electronic configuration of chromium. So here the chromium has 24 electrons. Here the chromium has 24 electrons. So first 2 electron will goes to 1s, then 2s, then 2p, 3s, 3p, 6. Okay. Now the next electron will go to next to 4s. Now the next electron after 4s it will go to 3d because 4p it has n plus l equals 5. So since 3d has got lower value of n, therefore the next electron will go to 3d. So it goes to 3d. So 4 electrons are left. So the next 4 electrons should go to 3d. But this electronic configuration is wrong. Okay? Correct electronic configuration is here. The correct electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d5. We discussed just now that half-filled orbitals are very stable than the orbitals which are not half-filled or completely filled. Suppose this is the 3d orbital, okay? This is 3d orbital. And this is the 4s orbital. 4s and 3d. Okay, so the electronic configuration should have been this. Okay, but since the addition of one electron over here will make 3d orbital half filled, okay, and relatively more stable than this configuration, therefore one electron jumps from this place and gets here, making this particular arrangement more stable. Okay, so this is the more stable arrangement. So therefore the correct electronic configuration for chromium is this. Fine. Now in case of copper, since copper's copper's electronic configuration should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So far it has been 20. Now 9 are left. It should have been 3d9. Okay. But again, this is wrong. The correct electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d10. Using same arguments, this is 4s, this is 3d. Now this arrangement, okay, this is this one, this arrangement. So this arrangement is less stable, okay, than this arrangement. Therefore, if one electron jumps from 4s orbital to 3d orbital, then this particular arrangement becomes more stable. Okay, so therefore the correct electronic structure for copper is this, not this. So that's all for this video, and with this we have finished the theoretical part of atomic structure. In our next video we will discuss the question.